When you look at a vibrant nighttime cityscape, it's easy to assume the magic is entirely in the electricity surging through those intricate glass tubes. We associate that famous, colorful aesthetic with a single word: neon. Yet the vast majority of the diverse, glowing signs lighting up the strip rely on completely different gases to create their colors. In its true natural state, element number 10 on the periodic table is completely invisible. It has no color, no odor, and if you filled an entire room with pure neon gas, you wouldn't be able to detect it with your own senses. Despite remaining entirely unseen, this phantom gas has become a highly sought-after resource, driving a massive global supply chain. Why do we spend immense capital extracting, refining, and purifying an invisible substance by the ton, only to pump it deep into the most expensive, tightly controlled manufacturing facilities ever built? Neon functions as a critical industrial pillar, supporting the high-tech infrastructure of the modern world from behind factory walls. To understand exactly how an invisible gas powers modern industry, we have to look inside the atom itself, starting with the specific mechanics that cause pure neon to produce its famous orange-red light. Think of a neon atom as a tiny building with elevators. When a strong electrical current strikes the gas, the electrons orbiting the nucleus absorb that energy and are forced outward into higher, more energetic orbits. But those electrons cannot hold that position for long. As they inevitably return to their stable positions, they release that absorbed energy as photons. For pure neon, those photons always emerge as a brilliant orange-red light. This electrical reaction produces the light, but the element's industrial utility depends on its permanent chemical architecture. If we examine neon's outermost shell, we find a structure in perfect equilibrium. It holds the absolute maximum number of electrons it can carry. Chemists classify elements with this complete structure as noble gases. Because its shell is already full, neon has absolutely zero desire to react with other elements. It simply refuses to gain, lose, or share electrons. It will not bond, it will not burn. This absolute chemical indifference allows neon to exist in volatile environments without ever changing its form or interfering with the process. High-end industrial manufacturing requires working under extremely volatile conditions. At the microscopic level, a single rogue chemical bond or trace amount of oxygen can destroy delicate equipment in a fraction of a second. To prevent those disasters, massive storage facilities are built exclusively to capture, isolate, and pressurize this completely unreactive gas. Because it won't react, neon provides an incredibly stable medium for advanced research lasers. It allows high-intensity light beams to travel through experimental equipment without interference. But its most demanding role happens inside semiconductor factories, where the gas acts as both a cryogenic coolant and a perfectly safe atmosphere for chip fabrication. Building computer chips means carving microscopic pathways into vulnerable silicon wafers. Inside these intense cleanroom environments, neon is pumped in to act as an impenetrable protective shield, ensuring no outside elements can bond with or ruin the fragile circuitry. It operates as an invisible guardian, allowing the delicate creation of modern electronics to happen safely. The results of that microscopic protection eventually leave the cleanroom and make their way directly into your daily routine. The complex processors running your laptop, smartphone, and data servers exist largely because neon provided a flawless, stable environment during their delicate assembly. We tend to focus on elements that do dramatic things, the ones that explode, burn, or fuel aggressive chemical reactions. And yet, scientific utility takes many forms. For decades, skilled glassworkers bent this gas into colorful, glowing signs that defined the aesthetic of our cities. Today, its most critical work happens silently, locked deep inside manufacturing plants. Element 10 proves that you don't need to be highly reactive to be useful. Its absolute, invisible stability is quietly powering the technology we rely on every day.